fin dies that are very analogous to these if you don't have these exact specifications. And in the chart over on the right, we've placed tonnages. The first column there has 1100 O-temper, which is, if you go back again 25 or 30 years ago, that was far and away around the world the most typical fin stock that was being used. It's pure aluminum, it's very easy to draw, it's very forgiving to work with, and it was easy for people. Maybe 20 years ago, we started to see higher tempered materials being used, and that typically was done as a way to minimize damage in coil handling. The stronger the fin is, the less damage is likely to be caused as you're moving the coil around the shop. And also, a stronger fin is easier to wash when it's in the field. There's some really good reasons to use stronger fin material. But as the tensile strength of the material increases, it also increases the work the press has to do to create the fin. So if we go to the top of the chart there and look at die number 1, we've got a 42-ton situation with 1100 O-temper that then rises to 52 tons as we go to quarter hard H22, 62 tons at half hard H24, 68 tons at H26. And then the final category you see there is 8000 series. In the 8000 series, aluminums were created to improve the drawability at higher tempers. And the drawability improvement is because the material, the aluminum, actually contains some iron, so its tensile strength has gone up a lot, but it means you can also draw that material without tearing it apart. But look at what happens to the tonnage. By moving from 1100 O-temper at 42 tons, we've almost doubled the tonnage required for that fin die as we move to an 8000 series, an 8006 or 8011 H26 material. Now, hardly anybody anywhere that we're aware of has made that jump in a single move. This has been something that they've taken, this has been a 20-year progression for many customers. And it's oftentimes, when I present this information, an aha moment for them, because they've seen over the years greater and greater difficulty getting a good collar base, especially out in the middle of a die. And the reason for that is because they've been progressively overloading their presses without the knowledge that that was happening. So our solution to that problem has been to create a new family of presses that's really designed to deal with these higher tensile fin materials and also the tighter patterns, because as the pattern gets tighter, you end up with less and less area on the fin that is not affected by either piercing or forming or cutting. Really, every part of the fin has some kind of work done to it as you get down to 5 millimeter, 4 millimeter, and 3 millimeter fin patterns. On this chart, the FP3 is a 100-ton press, so you can see what's possible with a 100-ton press, highlighted in blue. The FP1000, we'll talk about a little bit later, is our replacement for the FP3 press. Again, it can obviously do all of the blue, but also what you see in orange. And then the FP1400 right now is the top of our press family, and as you can see, the FP1400 is capable of doing almost everything that we see out in the field today in terms of stamping requirements for large fin dies. Now this is another chart that will show you what happens to the various classes of presses as you move from that 1100 AL H22 all the way up to an 8011 with H26. The first column is our new FP400 press. It has 50% more tonnage than the FP1 that it replaces. And as you can see, there are no issues for the FP400 as we move from what was common years ago to what's common today. The second two presses you see there, the 2B36 and the 2B48, are 60-ton presses. And there are lots and lots of 60-ton presses all over the world making fins today. Again, if you look at the dies in the 1100 category, 2B36 and 2B48 No problems, no issues. We're running a 36-row 4-progression, a 40-row 4-progression, no issues with closing, no issues with collar base formation. But as you come across to the 8011 H26 series, you have serious problems. Now we're having to back that 36-inch press down to a 30-row die to stay inside of the tonnage capabilities. And look at what we've lost in terms of the number of holes produced. We dropped from 900 to 750. And we have an even larger drop in our 48-inch press because we also have to back it down from 40 rows to 30 rows, which cuts our whole production from 1,000 down to 750. Now, if we look at a generic 100-ton press over here on the 1100 side, we can manage a 60-row die. But as we come across here with a generic 100-ton press, we have to drop back to a 48-row die, which, again, you know, we take a large hit in our production capacities. We have two excellent solutions now for people who find themselves in that quandary. The FP1000, which is a 1,000 kilonewton press, with that same kind of material, is capable of continuing to operate that 60-row fin die and continuing to maintain the same output that was possible with the 1100 alloy. And then we have the 1400 press, which is capable of operating a 72-row die in those same conditions at 132 tons and producing 50% more than that generic 100-ton press. With 5 millimeter, you have an even more difficult situation because, as we said earlier, as those holes get closer together, more and more of the fin surface, virtually all of the fin surface, is affected by cutting, bending, forming, piercing, something. There are no unaffected areas. Again, on our FP400, we have no issues and no worries as we transition across because it's a 45-ton press, and you've got 31 tons over here. The 60-ton presses, same kind of problem that we saw. We're going to struggle. You see, we've kept 2 progression dies here. In our earlier example, we had 4 progression dies, and you can certainly see here if we tried to do a 4 progression, that just wouldn't even be a possibility. Our generic 100-ton press is capable of a 60-row die at 4 progression, 83 tons, which is right at the edge of most press builders' comfort factor in terms of producing a high-quality fin. As we come across, we're compromised over here. We have to drop back to a 40-row die to make that work in our generic 100-ton, and look at what happens to our production. With the FP1000, we can still sustain a 54-row die, and at nearly the same production that we can manage with the generic 100-ton with the 1100 and the lower temper alloy. But by moving to a 1400, we really can take the lid off. We can go a 72-row 4 progression and produce 1,200 holes per minute, or we can use a 6 progression die with 54 rows at 160 tons and be at 1,350. Large productivity increases and the same floor space. The first press we want to talk about in our new family of presses is the FP400. This is a direct replacement for the FP1 presses and the FP1A presses that many of you have today on your factory floors. Fits you have are numerous. The press has 50% more tonnage than the old FP1s. It has a lower initial cost. It has greatly improved die takeout capabilities. You can go right out the back with a fin die. It has greatly improved performance. The line equipment has been redesigned. There's less vibration. It's much easier to lace. It's much easier to maintain. A great improvement over the previous generation. The FP1000 is the new replacement for the FP3 fin press. it's the same basic press layout. It's a 4-point twin crank design. It's capable of going up to a 3-inch stroke, so if you have those applications that are very high collar fins, no problem getting you the stroke you need to accomplish what you need to accomplish. One of the real improvements is it's dynamically balanced. Up on the eccentric shafts in the press, there are counterweights. So as the slide moves down, the counterweights are moving up to counterbalance the forces of the slide and the punch holder. So we rate this press to be capable of operating as fast as 400 strokes per minute with large fin dies, which is a mighty leap forward. Also, this press is 1,000 kilonewtons. It's 112 tons, and it's designed so that it can actually have a die of that tonnage in it and still close well. We've used finite element analysis to design the press. It's much heavier than the FP3 that replaces, and all that extra iron is in the right place to make sure that when your die comes closed, it comes closed with authority. And topping the press family today is the FP1400. It's the same die area as the FP1000, but it has a 1,400 kilonewton or 160-ton rating. This is the right press, as you can remember from the previous chart. If you know you're going to be doing 5 millimeter, or you know you're going to be using 8000 series fin stocks at the higher tempers, this press will get the job done, and it future-proofs you in a way that other presses just cannot do today. Some of the design features of the press that you really can't see here: the slide of the press is made of a special high nodularity cast iron that's 50% stronger in bending than the iron is typically used in the rest of the press and in other presses, and that means everything. When you have to make sure that out in the middle of that die you want to have features as sharp and as well formed as you have on the edge of the die. You want to have collar bases that are well formed. That's the kind of thing you need to do. The 1400 is also balanced, so again it's cleared for operations up to 400 strokes a minute with large dies. Now, one of the new improvements that both the 1000 and the 1400 share is a front mount servo feed system. It's a huge improvement over the old mechanical feed systems on our presses. With the old system, if someone wasn't careful in setup and didn't pay attention to what they were doing, it was not a difficult thing to raise the crown of the press and literally tear the feed system apart. Not a possibility here anymore. It also was possible on it's also possible on a mechanical feed press to set it up wrong so that the feed is trying to do something that's not mechanically possible, and suddenly all that flywheel energy is injected into the feed system and it tears it apart. With the servo feed, that's not a possibility. They're completely independent. The progression changer is gone. The servo feed does its own progression changing, which means die access is much easier. The whole progression changer frame is gone. There's nothing anymore to reach over on the side of the press, and operators, our field report from operators are they just love that. The press operator can now control the fin length right from the touch screen, which again is something that they really like. There's no torsional twist with this system. You'll remember or have observed that our old mechanical feeds drove from one side, and what that did is you would end up with driveline windup. That shaft would twist, so these two arms would actually get out of time one with another as it twisted back and forth. This is fed from the center. You have balanced forces, and that material is going to be pulled straight forward. No issues, no worries. It's going to be where you want it when you need it to be there. We've also built in at the end of each one of these arms an 11 thousandths eccentric adjustment here, so that your setup people can dial that feed bar in to be just precisely dead accurate to the die, so that again you're going to have a much better feed situation. The outboard supports are also integrated into this and are tremendously stronger and more capable than our older outboard support was. So when you have dies whose bolster and die shoe extend beyond the bed area of the press, they have excellent support now. Another improvement that's available on all of our presses is our new electrostatic lubricator. It makes for a much cleaner machine and work environment. We're no longer spraying lubricant all over everywhere, which is pretty much the case with most systems that are out there in the world today. We're putting a metered amount of lubricant on the upper and lower areas of the fin stock in a very uniform process. Customers have reported back to us reduction in oil consumption as high as 90%, and tooling life improvements as high as 30%. So we think this is a great solution for people, especially if you're in this area where VOCs are a problem in your factory, because you can dramatically reduce your VOCs by using this kind of system compared to a typical lubrication system. Now let's talk a little bit about the challenges of placing fins on stacker rods, fin movement on stacker rods, the increasing weight of higher density fin packs, and how do we get those fins off once they're there. We'll first talk about the suction unit. This is the new suction unit that's standard now on the FP1000, FP1400 presses. You can see here that we have what we call a tap-down style suction sheet, where there are servoed sections of the sheet that move to actually place the fins down on top of the stacker rods. This is a new, much more efficient design blower unit. With a 3 horsepower motor now, we can actually move more air and provide more suction than we used to with a 5 horsepower motor, so much more efficient, less energy consumption. We have a redesigned door system that is much more reliable, much more durable. It does a better job for us. And we also have, your set of people will love this, on all 4 corners, these turnbuckles, which allow you to get very precise alignment of the suction sheet to the cutoff and the fin die, which greatly aids in fin production. Another feature they'll really enjoy are these THK rails up here, which allow you to quickly and easily roll the whole suction unit back away from the cutoff so that you can get in there and work on your cutoff as you may need to and want to. We have a new style of stacker rod, and all of the new stackers that come with the FP1000, the 1400 come standard with these rods. They're made of stainless steel that's heat treated. It's about 5 times as stiff and bending as the old rods we used to use. Because it's stainless, the durability is outstanding, the memory is outstanding. The surface finish is electro-polished. You just don't have any troubles with fins hanging up on these rods. And the tip geometry also helps with that. We call this our double delta tip, whereas the old style rods were a continuous point just at the end of the rod. These rods, as you can see, don't get to full diameter until you're back about 40 millimeters away from the tip of the rod, because we found that if we can get the fin started on the end of the rod, it will eventually get down here and onto full diameter and down the rod. The surface finish and the fact that these are stainless steel is a huge benefit for customers everywhere, because steel rusts, and most people today are using some sort of evaporative lubricant that provides no protection to the stacker rods at all, especially in unattended situations like, if you're gone over the weekend. Well, the reality is with steel, if it's not protected by oil, any humidity above 50% relative humidity will cause the rods to rust. And we see that everywhere we go, rusty rods. And even if the operators come in there on Monday morning with their Scotch-Brites and try to clean the rust off the outside of the rods, what's left is a cankered, rough surface on the outside of the rods. Fins are not going to want to slide down that, and you're going to have jams and loss of production. And that's just not going to be a problem with the new stainless steel double delta stacker rods. We also had to redesign our stacker unit. It's a tremendous improvement over the elevator stackers that we've been producing for many years. It's about 3 times as stiff and bending. Those of you who are familiar with our stackers, you can see here that almost everything has changed. We've got THK rails down here now that make it very easy for one person to do a setup. You can come over to the control panel and you can lower the stacker tooling down, and there's a little detent here that then is engaged, which unlocks the rod holder, and it's very easy for one person from one side now to move the rod holder or they need to move it for their setup. The motors and the chains and the elevators have been upgraded so that even if you've got 1,000 pounds of fins on your stacker, which is not a hard thing to accomplish if you're talking about fin packs that are 26 fins per inch or higher, no problem using that elevator to lift the fin pack, so it's easy for your people to get those fins off of the rods. The stacker base is now fully supported. As you can see looking down here, those THK rails are never in a place where they aren't supported well by the structure of the stacker. Larger, easier to use levelers in 6 places. Just a tremendous improvement. The rod location is just outstanding, and customers who have these have just been ecstatic in their praise of this new stacker design. Now let's talk a little bit about the tubing side and some of the challenges we can run into with processing small diameter tooling. Most of you have hydraulic benders, and those benders have straightening rolls, and sometimes they have cross-axis straightening rolls as well as standard straightening rolls. Well, every time you go through a pair of rollers, you work harden the tubing. And work hardening the tubing is not what you want to be doing really when you're getting ready to bend the tubing, because when you bend, you want to have maximum ductility. And work hardening before it gets there is not a feature. The straightness of the hairpins is really critical. The smaller the diameter of the tubing is, the more you care about the straightness so that you can lace. Peg leg is also a really big deal. You know, when you get to the expander, you don't want to have any peg leg when you come down with that tooling, because you're at risk of splitting the tubes with stick out. And here's our solution. The Triumph hairpin bender is without question the finest hairpin bender in the world today. It's mostly electric. The only hydraulics left on the machine are for clamping, and so the energy efficiency is much improved over our previous hairpin bender design. It has, at a minimum, a 70% increase in productivity compared to our hydraulic bender or other hydraulic benders that are out there in the field today. It produces more tubes per cycle. You can see here, if we're talking about 3/8 of an inch or smaller diameters, we're producing 8 tubes at a time. When we go above 3/8 to 1/2 inch and 5/8, we produce 4 tubes at a time. The floor space is about 30% less than a hydraulic bender of the same length capabilities. It costs less than our old bender. The quality improvement is tremendous. Peg leg is something that virtually is gone on the Triumph bender, and we've gotten just spectacular SBC results in from customers around the world when it comes to the Triumph benders. Matter of fact, one of the stories I like to share with people is when we had the first prototype machine out in the field, it was being used by a manufacturer that makes hairpins for a living. And they were supplying a large U.S. producer of coils, and they supplied some hairpins, and the SBC information was along with it, and the engineer called back to the manufacturing site and said, there's something wrong with your SBC data here. This can't possibly be correct. And the producer said, well, I'll tell you what, you measure the hairpins yourself, and then you call me back. And so he did. And he called the manufacturer back up and said, how in the heck did you ever accomplish this? I've never seen numbers like this. I wouldn't have believed him if I wouldn't have measured them myself. And the guy said, it's a new hairpin bender from Oak. It's just amazing. It's great. Well, one of the things the hairpin bender, the new Triumph bender, solves also is the ongoing war that's happening between your night shift and day shift. Because every factory I go into everywhere, the day shift's view of the night shift is they don't know how to adjust their straighteners. And it's a continuing war. Well, those straightening rollers are gone on the Triumph bender because now we stretch straighten the tubing. There's no belts, which if you're running aluminum is a huge benefit, because any of you who are out there right now running aluminum realize it takes very little time at all before you have aluminum oxide and oil slathered all over your feed belts, and they're slipping and your people are going crazy trying to deal with peg leg issues and trying to deal with issues of production, trying to maintain production. With the Triumph bender, aluminum is no issue whatsoever because we're using a collet clamp system to positively grab the tubing, and it's just no issue. Another huge benefit of the Triumph bender is what happens when you buy a machine. Oftentimes, you know, the engineering group will go to the product development people and say, okay, we're going to buy a new hairpin bender. What's the longest hairpin that we're going to manufacture? And they'll say, well, 2 meters. You know, we're never going to make a hairpin longer than 2 meters. And what happens again and again is someone then buys a 2-meter hairpin bender, and 3 weeks later, the product development people are out on the floor saying, we really need 2.5-meter hairpins. Well, with anybody else's hairpin bender, that's a huge problem. It's not a problem with the yoke bender. If you start out with a 2-meter machine like you see down here, and suddenly your product development people say you need to make 4-meter hairpins, all you have to do is come back to Oak and get 2 more sections of runout table, and that 4-meter boom, and your 2-meter hairpin bender suddenly became a 4-meter hairpin bender. And oh, by the way, with that 4-meter boom on there, you can still make 1-meter, 2-meter, 3-meter hairpins. No problem. Another huge advantage of the Triumph bender is setup time. With most hydraulic benders, if you change the length of the hairpin, that might be a 10, 15, 20, or even 30-minute changeover. On the Triumph bender, it's seconds. It takes like 10 seconds to change the length of the hairpin. That's all the time it takes. On a hydraulic bender, if suddenly somebody wants to change from making 3/8 by 1 to 5-millimeter tubing, that's probably going to be a 3-hour changeover. On the Triumph bender, if you have a pre-tooled boom there on a boom rack beside the machine and what we call a tooling sandwich that drops in, you can completely change over the Triumph bender in 20 minutes. Bend centers, everything. Diameters, everything. So it's just a spectacular improvement. This is the first time I've been working, as Tim told you in the introduction, I've been working at Burrow Tool part-time since 1972. And this is the first time we have ever built a machine that could go onto someone's floor and replace a brand new hydraulic machine of ours and have a payback of a year or less. It's just amazing. Great, great machine. And then in the question we asked beforehand, the biggest challenge that people expected to face with small diameter is expansion. And it is challenging. It's probably not going to be possible to modify any expanders on your floor today to take them from 3/8 of an inch to 5-millimeter mechanical expanders. It's just too hard. And it's too hard for several reasons. The first is the expander rods get so small when you're talking about 5-millimeter tubing that you have to have a lot more guide plates to maintain the straightness of your rods. And so those probably aren't going to fit in your current expander. The other thing that has to be much, much more accurate is the location of the tooling in the machine. So we now use on a new expander, there's THK rails that are used to position the plates and the tooling, because if you think about the kind of target you have, you've only got a 200 thousandths diameter hole with a 5-millimeter tube that you have to get the tooling into. So it's a much more difficult proposition than it used to be back in the days when you were doing 3/8 or even 1/2 inch. And you know, we would also tell people if they're going to do 5-millimeter, the hairpins that you want to have in this expander should be the hairpins that come out of that Triumph bender, because especially with enhanced tubing, you don't want to have any stick out whatsoever when you come down and try to do that final expansion. for fear that you're going to split or crush your tubes because the heights are not all the same. Well, that concludes my formal presentation. I'd be happy to answer any questions anyone has.
Newell, we do have a couple of questions that have been submitted. One of them has to do with calculating the tonnage. As you mentioned earlier, one of the very first screens. And can you address that just for a few minutes?
Yeah, we've got a spreadsheet that we use here to do that work. And if you have any questions about any fins you have, we'd be very happy to either share that tool with you, or you can send us the information about your fin or a fin drawing. We'd be very happy to come back and say, here's the tonnage required for the fin that you're currently trying to produce with the materials you're trying to produce them with.
Okay, another question had to do with handling the hairpins once they've been created, especially on the very small diameters. Anything that we have seen or experienced that may help with that material movement?
You know, most of the people that I see doing it are just putting them in tubs, and they carry the tub to the lacing table. And if they're 5mm hairpins, if the length is I'll say, you know, 1 to 1.5 meters, it's one person doing the lacing. And if it's 2 meters or longer, a lot of times there will be two people that are working together doing the lacing of those very small diameter hairpins.
Another question, can we improve an electrostatic lubricator that is in an old FP1? We would probably, the person that asked that question, we probably need a little bit more information about that before we can answer that.
Yeah, I would tell them to get the press serial number and contact our support people, and they'd be happy to work with them on that issue.
Another question, what is the longest typical hairpin that is right now being made in production with 5mm?
The longest one that's produced in quantities that I can think of is 110 inches. That's the longest one I'm aware of right now today.
Okay. Let's see, looking at some. What thicknesses, I'm guessing this is tube diameter, or the wall thickness is recommended for small diameter tubes. I'm guessing that's what that question is.
Yeah,
so the wall thickness.
Yeah, that's gonna depend on what you're using as a refrigerant, because the refrigerants have different pressures. So that's just something that, you know, your product design people are going to have to figure out in conjunction with your tubing supplier.
Okay, there's a follow-up to that. What about the typical minimum wall thickness to prevent damage in tube handling? What experience have we had with that?
I'm not familiar with people experiencing much in the way of damage in tube handling. That's kind of a new concept to me. So I guess I can't respond to that.
Okay, are we working with any 4mm and 3mm tubing size at the moment?
We've done 4mm before. We haven't done 3. I put 3mm on there because as I look at what's happened in the past and I look at the future, there are already 4mm production coils being manufactured in Asia, and it's not hard for me to, I know there's been research coils made in 3mm. It's not hard for me to imagine that there will be some production coils in 3mm too.
Okay, here's another question. Are there any limitations regarding the fin profile in combination with smaller tube diameters?
Not that I can think of, other than you do have some limitations in formability of materials. You know, they're depending on the quality of the fin stock. There's things you can do with drawing, and there's things you can do with bending that you couldn't do with some other fin stocks. But that's I guess the only comment I would make along those lines.
Okay. Another question: any special devices that we know of for lacing those 110-inch hairpins that you mentioned?
No.
Somebody else wrote in that they're doing 144-inch hairpins. Doesn't mention the tube diameter they're using, though. Okay, what is the most commonly used aluminum alloy, and what hardness? Do we know what is typically used out there?
Are we talking about fin stock right now?
Fin stock.
Okay. As I traveled around the world, the most common thing I'm seeing now is an 8000 series, 8006 or 8011. It has, in the last 2 or 3 years, it has dramatically replaced the 3000 series and the 1100 and 1200 series in lots and lots of manufacturers. And you know, when I ask the question why, the answer I usually get is, well, you know, we have less fin handling damage when we're using this strong material and the strong fin. And sometimes, too, they were having tearing issues trying to get the collar heights they wanted with the 1100, the 1200, the 3102, and this solved that problem for them, too.
Yeah, tearing issues also can come with pulling it through. So, okay, another question. Are we planning on building a smaller press to accommodate the smaller tubing that seems to be the future?
Well, we have no plans right now to make a press smaller than the FP400. And the FP400 is designed for fairly small dies, so you know, I'm not sure that a smaller press would be much of a benefit to most of our customers.
Yeah, this was the question specifically talked about somebody who's making replacement coils.
Yeah, okay. No, right now there are no plans to make a press smaller than the FP400.
Okay, another question. What percentage of the new Triumph bender sales are for 5mm tube or smaller in the U.S.? Do we know the answer to that?
You know, I don't. We can, well, I can look at that and then, you know, put an answer online for you.
Well, thank you very much for your questions. We will go ahead and close down the webinar now, and it will be available. A recorded version of this will be available online on our website, and you will, anybody who signed up for the webinar will receive an email with the link to that recorded presentation. It will include the answers to all the questions, and we will also make the questions available to everybody. So thank you so very much for attending the webinar, and we hope that you have less snow wherever you are than we have here. Thanks.